Hey guys, Mr. B here. Welcome to our final edition of the atom and periodic table, objective number 3. If you have your matrix, you probably want to get that out because you have these questions down here at the bottom. We're focusing on this row at the bottom here. You're going to answer these questions, these essential questions. And of course, here's our objective. Today we're going to focus on protons and how protons give an element its identity. And we're going to take a look at how valence electrons affect the chemical properties of an element. And then at the end, we're going to talk a little bit about mass and size. So let's get started right away in talking about the elements and their identity. We have a cow here having a bit of an identity crisis. I think he thinks he's a cat. Unlike this cow, elements do not have an identity crisis. Elements know exactly who they are, and we're going to talk about why they have the properties they have and the identity that they have. And so you remember from your Wix on the periodic table, you talked a little bit about the three major groups, the metals, the metalloids, and the non-metals. The biggest group being the metals to the left here, and how they're shiny, malleable, good conductors of heat and electricity. Non-metals being dull, brittle, poor conductors of heat and electricity, and then metalloids having characteristics of both. What gives these elements these properties? What makes these elements what they are? And that's kind of the question we're wanting to answer. What gives an element its identity? Well, turns out it's its proton. Let's take a look at hydrogen. Hydrogen, here's an example of the hydrogen atom. Three versions of hydrogen, as a matter of fact. You'll notice that that each of these atoms have differing numbers of neutrons. Atoms can actually exist in nature with extra or fewer neutrons than the normal atom. They're called isotopes. And in these atoms above, all three of them have different numbers of neutrons and different masses. This first one is the normal one we study most of the time. One proton, one electron, has an atomic number of 1 and a mass of 1. Here, the mass is increased to 2 because we've added a neutron. Remember, protons have 1 atomic mass unit, neutrons have 2. And so to the right still, the furthest one over, we have 2 neutrons and 1 proton, giving hydrogen a mass of 3. But guess what? It's still hydrogen. Why is it still hydrogen? Because it only has 1 proton. And a proton is what truly gives an atom its identity. So no matter what we do to the neutrons, hydrogen is hydrogen because of its proton. Another example, in nature, some of these atoms exist in what we call ions, where they have a positive or a negative charge, which means, like in this example, we have, here's a neutral version of hydrogen, 1 proton, 1 electron. We're used to that one. But over here to the right, we have 1 proton, and the electron is now gone. So it's a positively charged ion because it has more protons than it does electrons, which is kind of interesting, but guess what? It's still hydrogen. Now, you don't have to know about ions, but what you do need to see is that even though the electrons have changed, it's still hydrogen. Why? Because hydrogen has 1 proton. You know, if we added even 1 proton to this model, it would no longer be hydrogen. It would be helium, because helium has 2 protons. So we can change the neutrons, we can change the electrons, but neither one of those changes the identity of the atom. It's the proton that changes its identity. Okay, let's talk a little bit about the reactivity and the chemical properties of an atom. You know, what makes some elements more reactive than others? In this example, I've got potassium to the left, and it's exploding just upon contact with water. They just threw a little bit of water in the bowl, and violent explosion occurs. And then comparatively, we have neon over to the right. Neon's a very stable gas that's used in signs and stores and things like that. And why do they feel comfortable using them in signs and stores? Because they're safe. They're very stable. In fact, just to get neon to glow like this, you have to excite those atoms with electricity. And even then, it's very stable. So what makes potassium violent and reactive, and what makes neon so stable? Well, that's what we're going to talk about. It has to do with what family they're in. You remember the families and groups from your periodic table objective or periodic table Wix, that the families are the vertical columns. There are 18 of them, starting here on the right with 1 all the way over here to 18. 18 families, and these are the vertical columns. And as you move down these families, elements get more reactive. If you remember from your periodic table video, this first family, the alkali metals, potassium, very reactive, as you saw in that picture, but cesium, francium, even more reactive because you're going further down. And so reactivity increases as you go from top to bottom. Now, reactivity is also changes as you move across the periods. Remember, periods are the rows, the horizontal rows. There are 7 of them. And just as a review, they do determine how many energy levels an atom has. Period 1 has 1 ring, period 2 has 2 rings or energy levels, so on and so forth. But reactivity changes as you go from, say, like neon over here in family 18, all the way over to lithium in family 1. Guess what happens to the reactivity? Well, it increases. And so these elements here in family 18 are very stable, and the elements, in fact, they're called noble gases, and because of their stability. And then all the way over to the left, you have the most reactive family on the periodic table, the alkali metals. So why does reactivity increase? And by the way, when we talk chemical properties, we're talking about the reactivity of an element. When we say chemical properties, we're saying how does this element react with other elements. The noble gases don't react with other elements. They're very stable. The alkali metals do react with other elements very violently sometimes, like you saw in the picture with potassium. Why? Well, because it has to do with how many electrons are in the last energy level or the outer energy level of an atom. Valence electrons are determined by what family an atom's in. These alkali metals, they're in family 1, and they have 1 valence electron. The next family, family 2, has 2. Now we're going to skip the transition metals because the pattern changes a little bit there. But in family 13, these atoms all have 3 valence electrons. Family 15 has 5. Family 16 has 6. Until you get to the noble gases, which have 8. So guess what makes the noble gases so stable? The fact that they have 8 valence electrons. In fact, the most you can have in an outer energy level of an atom, or the valence shell, is 8. And so because their valence shell is full, because they can't take any more valence electrons, they are stable. Unlike the alkali metals, which are very reactive, they only have 1 valence electron. And so as you go from the noble gases over to the alkali metals, the atoms get more and more reactive. I mean, basically what we're saying is the fewer valence electrons you have, the more reactive you are. Okay, so let's take a look at these valence electrons. How do valence electrons affect the reactivity of an element? So if you look over here at potassium, again, just to back up, it's in family 1 here, and it has 1 valence electron. And it wants to give this away. It wants to become stable. It wants 8 valence electrons just like neon has in order to be stable and not so reactive. And so it reacts quickly to get rid of that 1 valence electron so that its outer energy level can be full. Neon, on the other hand, doesn't need any more valence electron. It has 8. You can count them. 1, 2, 3, 4, 5, 6, 7, 8. And so it doesn't need any more. It's completely full. And so it's very stable. Again, the fewer valence electrons you have, the more reactive you are. All right. Oh, yeah, there's the little words that say that it has 8. All right, so now let's talk a little bit about mass, the masses of atoms. This is a pretty easy concept, really. When Mendeleev put the periodic table together, mass was one of the main driving factors in the way he organized. He wanted the elements to be in order of mass. And then, of course, that just naturally made them be in order of number of protons. Because remember, protons contribute to the mass of an element. 1 AMU, protons and neutrons for that matter. And so as you go across the periodic table from hydrogen to helium, the mass increases. And as you go down the periodic table from helium down to xenon and rhenium, or from hydrogen down to francium, you will notice the mass increases. It gets larger. It gets larger as you go from left to right and from top to bottom. I've kind of blown that up a little bit for you here. So you can see as you go from boron, again, that's starting at about family 13. As you go from boron at 10.8, it increases as you get to neon to 20, because it increases as you go from left to right. And then from helium, which has 4, atomic mass of 4, as you go down to xenon, it's 131. It gets much heavier as you go down. So elements have more mass as you go from left to right and from top to bottom. Pretty simple concept. All right, so now let's talk size. How large are atoms as you move across and down the periodic table? And I'm not talking about mass now. We're talking about physical size. And again, mass increases as you go from left to right. But it's a little different with size as you go from left to right on the periodic table. It actually decreases. Now that's kind of confusing. Why would if the element grows in mass, how does its size decrease? Well, remember, the atom's made up of mostly empty space. And so there's an attraction between the electrons in the electron cloud and the protons in the nucleus. That's what keeps electrons in orbit around the nucleus, as a matter of fact. And so because opposites attract like a magnet, that magnetism will pull those electrons in closer to the nucleus as you increase the number of protons and electrons. So it decreases slightly as you go from left to right. Now mass still increases. The mass doesn't decrease. The size, remember, it's size. Now as you go down the periodic table, size actually increases. You're like, well, you're adding protons, electrons, why doesn't it just keep getting smaller? Well, because there's limited amounts of empty space, and the fact is that you're just cramming so many protons, neutrons, and electrons into that atom, it has to get bigger. And so the more protons, neutrons, and electrons equal greater size as you move down the families. And I think that's probably the most important thing for you to remember here, is that size increases as you go down. I have a little picture that I wanted to show you. This kind of shows you that progression. As you go down the periodic table, size gets bigger, and it does get slightly smaller as you go from left to right. But I think the main point is that it gets bigger as you go down. I think that's what you really need to remember. All right, well, that's it for our talk. We do have an action item today. Using index card, we want you guys to make flashcards of the first 20 elements on the periodic table. And if you don't have index cards, cut up some paper. And on the front side, you're going to write sodium, or write the name of the element, as in this example, sodium. And then on the back side, the symbol. That way you guys can get used to, when we say look up sodium, you're not going, where's sodium? Because, Na doesn't look like sodium. And so if you kind of begin to commit to memory the symbol and the name, that's going to help you move in the periodic table much quicker, do better on tests, and all of that kind of stuff. So do it. Go write down the name and the symbol on an index card, name on the front, symbol on the back. You guys have been great. Thank you for your time. That's it for today.